In this video, we'll be looking at our notes for properties and proofs. So we're going to start off by looking at some properties that we'll use in geometric proofs. We're going to look at some properties we'll use with proofs for equations. We're actually going to try some equation proofs, and then we're going to do a couple geometric proofs using segments and angles since we've started covering those so far this year. So we first want to talk about what properties we can use when we are going to try to prove something true. So in our first line, we have the reflexive property. And the reflexive property essentially tells us that anything is equal to itself. And the way that I try to remember this one is I think of like reflective. When you look at yourself in the mirror, you're seeing your reflection. It kind of sounds like reflexive, and that's one of the ways I remember. For the transitive property of equality, it is the fact that if we have CD equals GH and GH equals RS, then that means that CD must also equal RS. Because GH was kind of the link between those two, they were both equal to GH, then we would know, well, GH is equal to itself, and therefore CD must be equal to RS as well if they were both equal to GH. So we can make that. It's kind of like our law of syllogism that we recently learned. Then we have our symmetric property of equality, which tells us that if BC equals RL, then we can also rewrite that same equation as RL equals BC. The order of an equation does not matter because of the symmetric property of equality. And then our last one that we'll see a lot is the substitution property of equality, and we're going to use this a lot. The substitution property is basically what it sounds like. You're going to be subbing in something for something else. So it's just like when you've learned how to evaluate an expression for a variable. In this case, in our example, it says if the measure of angle A equals 45 degrees, then 3 times the quantity measure of A should equal something. Well, we know that the measure of angle A is 45, so to get our answer, we'll just sub in 45, where we had measure of angle A in our expression, and 3 times 45 will make 135 degrees. So we're just subbing in that value. Then we have our proofs with equations properties that we're going to be looking at. And these are things you already know, but we're going to show them algebraically here with some variables. So for our addition property of equality, if you start with an equation that says A equals B, if I add C to one side and then add C to the other side, I'm still keeping it balanced because I did the same thing to both sides of the equation. Same with our subtraction property of equality. If I start with the equation A equals B and subtract C from both sides, I'm still left with the same thing. It's still equal. If A equals B, then AC equals BC is our multiplication property of equality because A and C are multiplying and B and C are multiplying here. And therefore, if I multiply by the same number on both sides, then I'm still going to be equal. For our division property of equality, we have a similar rule. The only restrictions on this is that C is not allowed to be 0 if we divide both sides by C. So it can be any number except 0. Remember, if we divide something by 0, we get an undefined value, so it would no longer be true. But any other number we could divide by and it would still be true. Then we have our distributive property, and remember that the distributive property takes the coefficient or term out front of the parentheses and distributes to both terms in the group. So the A term times B term is showing up here, AB, and then A times C term is over here, AC. Because there was a plus sign in between them, we will add those two terms together. Remember, the distributive property can also look something like this, where we get AB minus AC, and we just have a little bit different there because of the subtraction sign. Our additive identity property comes when you add 0 to something, you still get the same number. And our multiplicative identity happens when you multiply by 1 because it will not change the value. So now that we've had a review of the properties we can use, we're actually going to give these a try in our equation proofs. So in my first one, it says that I have an equation 5 times the quantity 2x minus 1 equals 9x plus 2. Now that is my given reason. Because that's the given equation, that's my reason for this. We're setting it up in this 2-column way of having statements on the left and reasons on the right. So every time you do a new statement, you need a new reason to go with it of why you're allowed to do that. It's kind of justifying your work. So we have our 10x minus 5 equals 9x plus 2 on the next line. So if I look at what happened to go from line 1 to line 2, the only thing I can see that happened is that I took this 5 and distributed it to the two terms. So the way that I got line 2 was by the distributive property, and that would be my reason for line 2. Then in my next line, I can see that I'm left with 10x equals 9x plus 7. So we got rid of the minus 5. Well, to undo minus 5 from each side, I would be adding 5 to both sides of the equation, meaning I'm using the addition property of equality. Then in my last step, I'm left with x equals 7. So if I got x equals 7, then what did I have to do to both sides to get that? Well, I subtracted that 9x from each side to leave me with x equals 7. So that would just be our subtraction property of equality. So this is kind of a fancy way of telling us all the steps that we already knew how to do for solving an equation, but we're just proving them at each part using these different properties. So if you want to try the next one, pause the video and try to fill it in yourself. Press play when you're ready to check. In my first problem, I can see that I have negative 2x minus 15 equals 8x minus 5. So what did I do to go from the first line to the second line? Well, I can see my negative 15 is still there, but the negative 2x is gone. Since it was a negative 2x, I needed to add 2x to both sides. So that means in my first step, I used the addition property of equality. Then in my next line, I have negative 10 equals 10x. So my 10x stayed where it was, but I no longer have this minus 5. So to get rid of minus 5, I would have had to add 5 to both sides, and that would, again, be my addition property of equality. I'm abbreviating this. You would want to make sure that you are writing out the entire property. Then we have our negative 10 equals 10x, went down to negative 1 equals x. So that got our x by itself. 10 had been multiplying x, so to do the opposite, we're going to divide by 10 on both sides. That would leave us with this negative 1 equals x. That means we use the division property of equality. And then our last step just took negative 1 equals x and changed it around to x equals negative 1. And that is just going to be our symmetric property. That tells us that we can rewrite any equation in the opposite direction and change the order of the equation there. All right, so next up, we have 2 more equation proofs. So again, if you'd like to try both of these and then check your work, feel free to pause the video and come back when you're ready. All right, so hopefully you were able to try these for our equations. In our first example, we had to solve the equation first. It was not given to us in all these lines this time. So in here, I'm showing you what I did at each step to get my equation. So let's talk through these steps here. I had 3x on both sides here. I added it in order to eliminate this negative 3x over here. So when I added that to each side, I was using the addition property of equality because I did it to each side of my equation. Then in my next step, I subtracted 5 in order to get my constants together on the left side. So when you're doing something to both sides, again, it's that operation, but it's that property of equality. So the subtraction property of equality. Next up, I divided by 5 on each side. So that's going to be my division property of equality because, again, it was to both sides. And then finally, I have my 3 equals x, and then I had x equals 3. So that was just using the symmetric property to solve. In my next equation, I'm going to, again, show all of the work that I did to get there. So I first had my term that was out front, so I'm going to have to use a property in order to give that away to each of them. So I have my distributive property showing up first. In my distributive property was because I was taking that negative 4 and giving it to every term inside the group. Then I added 4x to both sides, and I did that so that I could eliminate this over here. So that was my addition property of equality, because again, I did it on both sides. Then what I had was 16 plus 10 equals 12x plus 2, and I turned it into 26 equals 12x plus 2. So I didn't do something to both sides here. I just added 16 and 10. So that's not the addition property of equality. We can just claim the reason for that is that we were simplifying, or you could say combining like terms. Either one of those would be correct to justify what you did. Then I'm going to subtract 2 from both sides, and I'm doing that in order to eliminate my positive 2 constant there. So that was the subtraction property of equality, both sides there. Then I divided by 12 on both sides, so the division property of equality. And finally, I went from 2 equals x to x equals 2, and that was my symmetric property. We've seen how to do proofs with equations, and we feel kind of comfortable with that, knowing our background from solving equations last year. We're going to start digging into some geometric proofs. So the setup's going to be the same, but we're going to have some slightly different reasons because we're now going to be talking about geometry terms here. So some of the reasons that you'll be using in your geometric proofs are from concepts we've previously learned. So for example, I could cite the definition of midpoint as an example or as a reason in my proof. So the definition of midpoint, definition of angle bisector, definition of perpendicular, we've learned all those terms, so since we know the definitions of them, they can be reasons in our proof when we're writing a proof for geometry. We can also cite postulates. So far we've learned the segment addition postulate and the angle addition postulate. Those two postulates are statements that do not need to be proved, so we can use them in a proof. So let's try one of these out. The only thing that looks a little different here is that we have a given and a prove statement that we didn't see when we had our equations, and we also have a diagram. But otherwise, it still looks the same where we have our statements on the left and our reasons on our right. So in our first proof, we are given that C is the midpoint of segment AB and that the segment CB is congruent to the segment DE. We are trying to prove that AC, the segment, would be congruent to the segment DE. So in our first box on the left, we have our statement that C is the midpoint of segment AB and that segment CB is congruent to segment DE. Those two statements were given. You don't have to provide any other reason besides given because it was all in the given information. That will always be the first line of your proof. In the next line, we have that the segment AC is congruent to the segment CB. Well, when I look up here on my diagram, AC and CB are here, and I'm trying to say that they're congruent. Well, why am I allowed to say that? If I look back in the line above, the thing that I said up here is why I'm allowed to say it. I was told that in my given information that C is the midpoint of that, so therefore I'm using the definition of midpoint to make this claim. The definition of midpoint tells us that if you have a midpoint, then the two segments that are created by it are congruent. So AC must be congruent to CB. Then in my last line, I'm making my proof statement, the one that I was trying to prove. I'm saying that AC is congruent to DE. But why am I allowed to just jump to that? Let's see how that follows. I'm trying to claim that AC is congruent to DE. Above, I had said that AC was congruent to CB, and above that, I had said CB was congruent to DE. So green was congruent to blue. Green was also congruent to yellow. So therefore, since they are both congruent to green, then they must be congruent to each other. That is us using the law of substitution, and all we did was sub in each of those for each other. So I said that since AC was congruent to green, I can put DE in place of that. And since CB was congruent to DE, I could put AC in place of that. So I'm basically taking each of those individual segments and substituting them in for each other. Since green is equal to itself by the reflexive property, then I just use substitution here to make this final claim. In my next proof, I am given that the length of AC is equal to the length of BD. I'm asked to prove that the length of AB is equal to the length of CD. So here, these look a little different from the ones above. We had segments here being congruent to one another. Now we're talking about just AC and BD, which are the lengths of these segments if we were to take a ruler and measure them. And since they're lengths or numbers, they're equal, they're not congruent. Segments are congruent, lengths are equal. So I'm given that AC equals BD. That is my very first statement in my proof, so the reason is just given. In my next line, I'm saying that AB plus BC equals AC. When I look at my diagram, AB plus BC is equaling this entire segment AC. That is just our segment addition postulate. We learned that when two segments share the end point, and the point is between the two major endpoints A and C there, then we can claim that they add up to each other. So the segment addition postulate is my reason in this line. In my next line, I'm told that BC plus CD is equal to BD. Those are up here, and that will be because of my segment addition postulate again. And I'm allowed to repeat this reason 2 lines in a row because I was doing 2 different things here. I wasn't naming the same statement twice. I was naming 2 separate statements. They just happen to have the same reason because they come from the same rule there. So now that I'm on my next line, I can see that I've taken BC plus CD and I've set it equal to AC. So all I did here was I had BD up here. It was equal to AC. So all I'm doing is substituting AC in where BD was above because I know that they were equal because that was given. So that's just my substitution property, or just substitution for my reason. When I look at the next line, I can see that AC was equal to this BC plus CD. That's showing up right here. I can also see that AC was equal to AB plus BC. Since those are both AC and they are equal to each other, I am now taking this BC plus CD and AB plus BC and setting them equal to each other, and I'm using my transitive property to do that. So this is slightly different than substitution because I'm taking 2 terms that are being added together and replacing them where AC was. So when it's just subbing in one thing, like when I took BD and subbed it in for AC, or vice versa, I took AC and subbed it in for BD, that was substitution. But when I'm taking now, putting this pink expression in place of AC and this yellow expression in place of AC, that's taking an entire expression, and that's my transitive property. Then I have my final line. Well, I had AB plus BC equals BC plus CD, and somehow I made it down to AB equals CD. So what looks different? Well, these 2 BCs are both gone. Well, they were both added to that side originally, both sides, so if I subtract BC from each side, they'll be eliminated, and I'll be left with what I want. So that was just using our subtraction property of equality to get our final line of our proof here. All right, we're going to move on to our next proof. Here we are given that the angle 2 is congruent to the angle 3 in the diagram. We want to prove that the measure of angle 3 is also equal to the measure of angle 6. So my first statement was just given. Angle 2 is congruent to angle 3. Then it says angle 2 is congruent to angle 6. Okay, well, let's look at our diagram. Angle 2 is here, angle 6 is here. Those must be congruent because they are across from intersecting lines from each other. So that's the definition of vertical angles because those 2 angles were vertical to each other. So definition of vertical angles is our reason for why we're allowed to make that claim. In the next line, we are claiming that the angle 3 is congruent to the angle 6. Well, when we look at that, there's no really clear relationship in the diagram, so we can't use like vertical angles or supplementary at this point. We have to look back in the proof and see what we've done so far. We've said that angle 2 is congruent to angle 3, and angle 2 is congruent to angle 6. So if I want to just leave angle 6 where it was, all I'm doing here is substituting in angle 3 for angle 2 because they were also congruent. So that's just the use of the substitution property to make that line. In our last line then, we are saying we're going from the angle 3 is congruent to the angle 6, and we're making the claim that the measure of angle 3 is equal to the measure of angle 6, and that is just because of the definition of congruence. The definition of congruent things is that if 2 things are congruent, like angle measures or segments, then their measures must be equal. So their measure of angle 3 there must be equal to the measure of angle 6. In our last proof, it says we are given that the measure of angle 2 equals the measure of angle 1, and the measure of angle 3 equals the measure of angle 4. That is my given statement, and so the first reason in my proof will be given. In my next line, I can see that the measure of angle 1 plus the measure of angle 3 is called the measure of angle ABC. They're equal. Well, that's taking these 2 angles and adding them together. They have a common ray. So we are using the angle addition postulate in order to make that statement. In my next line, I'm claiming that the measure of angle 2 plus the measure of angle 4, so these 2 angles, equal the measure of angle DEF. same exact reason from above, the angle addition postulate allows us to add those together and write that equation. So that's just a postulate. We're allowed to rely on that. We don't have to provide any other reason but that postulate. So now that we've made those two claims, when I look down at my next line, I can see that I have everything from above, but I changed DEF to ABC. Well, why was I allowed to do that? We're saying we have 2 plus 4 is making ABC. We knew that 2 plus 4 made DEF. 2 was here, and it was equal to 1. So that means that I took my 1 here, where I had the measure of angle 1, and I replaced it with angle 2, and I put it down here. Then I had my angle 3 that was being added to angle 1, and I know that angle 3 is the same as angle 4, so I took angle 3 and I replaced it with angle 4. So I put this angle 4 in down here. And I'm basically rewriting this line, replacing the 2 for 1 and the 4 for 3. And I can leave my measure of angle ABC. So I used substitution twice for 2 separate terms there and said that I'm using the substitution property to get that. So in my final line, when I then can say that the measure of angle ABC is congruent to the measure of angle is equal to that, that's going to be the use of my transitive property. And that is because I am now saying that because these two angles added together both equal these two separate angles, so DEF and ABC, we can call those equal to each other because of the transitive property. Again, it's not just substitution because we're replacing the entire expression with that value. So this is our transitive property here. And we have now finished proving what they asked us to prove, that those two measures would be equal.